On July 1st, 2025, at approximately 3:17 in the morning, a telescope on a mountaintop in Chile recorded a faint smear of light crossing a field of background stars. The Atlas survey system flagged it almost immediately. The velocity was wrong. Not slightly wrong, not a rounding error, not a sensor glitch. It was catastrophically, unmistakably wrong for anything that belongs in our solar system. At 58 kilometers per second, whatever this thing was, it had arrived from somewhere else entirely. The Minor Planet Center confirmed it the very next day. In the span of less than 48 hours, humanity had found its third visitor from another star system, and for the first time in history, we had the instruments powerful enough to look at it properly. What those instruments would find over the next 12 months would quietly shake the deepest foundations of astrobiology, cosmic chemistry, and the oldest question our species has ever asked. Before we can understand what the James Webb Space Telescope found inside 3I Atlas, you need to understand what 3I Atlas actually is, because the naming alone tells a story. The designation starts with the number 3, meaning it is the third interstellar object ever confirmed passing through our solar system. The letter I stands simply for interstellar. Atlas is the name of the telescope network that caught it, a system built by NASA to scan the sky for asteroids that might threaten Earth. The first interstellar visitor, 1I Oumuamua, showed up in 2017 and was so bizarre, so unlike anything astronomers had ever seen, that serious scientific papers debated whether it might be artificial. It had no coma, no dust tail, no gas emissions, nothing a comet should have. Yet it accelerated in ways that gravity alone could not explain. The second visitor, 2II Borisov, arrived in 2019 and was far more cooperative. It behaved like a perfectly normal comet, which was actually its own kind of revelation because it suggested the chemistry that builds comets might be common across star systems. And then came 3I Atlas, and it blew both of them out of the water in terms of what it carried and what it told us. The object arrived from the direction of the constellation Sagittarius, that is the direction of the galactic center, the densely packed core of the Milky Way where stars are born and die far more frequently than in the quiet suburbs of our galaxy where our own sun lives. Within days of its discovery, it was already at about 670 million kilometers from the sun, well within the orbit of Jupiter, and it was headed inward fast. Astronomers around the world immediately understood the stakes. Unlike Oumuamua, which was only discovered after it had already passed perihelion and was on its way out, 3I Atlas had been caught on its way in. There was still time. There was a window, brief but real, to point every available instrument at this thing and drink in as much information as possible before it vanished forever. No interstellar visitor has ever returned. They come in on hyperbolic trajectories that do not loop back. Once 3I Atlas left, it would be gone from our solar system for eternity. That urgency defined everything that came next. The James Webb Space Telescope made its first observation of 3I Atlas in August 2025, just weeks after discovery. The team that pulled this off, led by astrochemist Martin Cordner of NASA's Goddard Space Flight Center, had to interrupt Webb's already packed observing schedule to do it. Webb is so heavily subscribed that getting time on it requires months of competition and peer review under normal circumstances. But nothing about 3I Atlas was normal, and the scientific leadership at NASA and ESA agreed. The telescope swiveled toward this incoming stranger, and its near-infrared spectrograph instrument, NIRSpec, went to work. What it found in August 2025 was already stunning. The ratio of carbon dioxide to water in the coma of 3I Atlas was 7, 6 with an uncertainty of only 0. 3, that ratio sat 4, 5 standard deviations above the average for all known long-period comets and Jupiter family comets in our own solar system. To put that in plain language, the comet was saturated with carbon dioxide in a way that had no precedent in anything ever found orbiting our sun. That measurement alone told astronomers that wherever 3I Atlas formed, it was not here. The chemistry of the cloud it condensed from was radically different from the chemistry of the cloud that built our planets, our comets, and our Earth. Through October and November of 2025, the comet reached perihelion, its closest point to our sun, on October 29th and 30th, at a distance of approximately 36 to 1, 4 astronomical units. That placed it just inside the orbit of Mars, which means it never actually came that close to our star in cosmic terms. But the solar heating it did receive during that passage was enough to do something extraordinary. The surface layers of this object, which had been frozen in the cold dark of interstellar space for billions of years, began to sublimate. Ice became gas. Ancient trapped molecules escaped into space in a swirling cloud called a coma, and that coma became a laboratory. Everything locked inside 3I Atlas, since before our sun existed, was suddenly available for telescopes to read. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer on its way to the outer solar system, managed to observe 3I Atlas using its cameras and spectrometers in November 2025. ESA's ExoMars Trace Gas Orbiter used its Cassis camera from Martian orbit to help refine the comet's trajectory, a remarkable improvisation given that the instrument was designed to photograph the surface of Mars from close range, not observe a fast-moving interstellar comet from across the solar system. The Hubble Space Telescope had already taken images as early as July 21, 2025, when the comet was 365 million kilometers from Earth. NASA's TESS spacecraft, the Transiting Exoplanet Survey Satellite, tracked 3I Atlas over multiple days in January 2026, studying the comet's brightness and rotational behavior. But of all the instruments trained on this object during its brief passage, none delivered data with anything close to the scientific weight of what James Webb and the Sphere-X Observatory produced in December 2025. The comet's closest approach to Earth came on December 19, 2025, when it passed within approximately 270 million kilometers of our planet. That is about 168 million miles, and to be clear, NASA confirmed at every stage that this object posed absolutely no threat to Earth. The trajectory was never ambiguous on that point, but the proximity gave telescopes their best possible geometry for observation, and the scientific teams seized the moment with everything they had. Just days after that closest approach, in the span of December 15th through 27, James Webb made a series of observations that would take months to fully analyze, but would ultimately change the conversation about interstellar objects forever. The Sphere-X Observatory, which had launched only in March 2025 and was still in its early operational phase, observed 3I Atlas between December 8th and 15th. Sphere-X is built to observe across more than 100 infrared wavelength channels simultaneously, and when it locked onto 3I Atlas, the data that came back was extraordinary in scope. The instrument detected water vapor, carbon dioxide, carbon monoxide, and dust in the coma. But what caught the attention of every astrobiologist paying attention was a suite of organic molecules built around carbon-hydrogen bonds that Sphere-X resolved spectroscopically. Specifically, the observatory detected methanol, formaldehyde, methane, and ethane. The production rate of these organic species was measured at approximately 14% relative to the water molecules being released. That number 14% is unusually high. In the comets we know from our own solar system, the organic fraction is almost always significantly lower. Something about 3I Atlas was rich in the kinds of carbon-hydrogen chemistry that, on Earth, we associate with the precursors to biology. Then came the Webb MIRI observations. Webb's mid-infrared instrument, MIRI, opens up a different set of molecular windows compared to NIRSpec. The mid-infrared range, covering wavelengths from roughly 5 to 28 micrometers, probes molecular transitions that other instruments either miss entirely or cannot cleanly separate from background noise. On December 15th and 16th, when 3I Atlas was approximately 329 million kilometers from the Sun, Webb's MIRI captured the first ever direct detection of methane in any interstellar object. This was a world-first measurement. The methane production rate was determined to be approximately 2 times 10 to the power of 26 molecules per second. On a follow-up observation on December 27th, when the comet had moved to 54 astronomical units from the Sun, the rate had declined slightly but remained robust. A paper detailing these MIRI results, authored by Matthew Belyakoff, Ian Wong, Bryce Bolin, and colleagues at Caltech, JPL, and the Space Telescope Science Institute, was published in the astrophysical journal Letters on April 8, 2026. Now, why does methane matter so much that its detection in an interstellar object warranted both a dedicated peer-reviewed paper and widespread scientific discussion bordering on something far more significant? The answer lies in what methane tells us and what it doesn't. Methane is a molecule of one carbon atom bonded to 4 hydrogen atoms, nothing structurally exotic. But on Earth, the overwhelming source of atmospheric methane is biological. Living organisms, primarily methanogens, which are microbes that thrive in oxygen-poor environments, produce methane as a metabolic byproduct. Methane is also produced geologically, and in comets from our solar system it is produced photochemically through the action of radiation on ice. But the timing of the methane emergence in 3I Atlas complicated the simple photochemical explanation in ways that scientists could not ignore. The detailed spectroscopy showed that methane was essentially absent in 3I Atlas's early outgassing phase, which Webb had observed back in August 2025 before perihelion. Methane did not appear until after perihelion, after the comet had rounded the Sun and the deeper internal layers had been progressively exposed by solar heating. This delayed appearance indicated that methane-bearing material was buried beneath an outer shell that had been depleted of the most volatile compounds during billions of years of exposure to cosmic rays and galactic radiation in interstellar space. The methane was buried, preserved, protected. When solar heating finally fractured the outer insulating layers and reached those buried reserves, the methane escaped in a measurable plume. The paper by Belyakov and colleagues described this as an unusual volatile inventory that, together with the carbon dioxide to water and methane to water ratios, painted a picture of a comet whose internal stratification had been preserved across cosmic timescales in ways that challenge assumptions about how interstellar objects evolve. Avi Loeb of Harvard, who has made it his scientific mission since Oumuamua to push the boundaries of what we are willing to consider when it comes to interstellar objects, published a detailed theoretical analysis in June 2026 titled, "Was Methane a Signature of Life in 3I Atlas?" The paper combined SphereX and Webb data and examined two distinct hypotheses through the lens of what scientists call panspermia, the idea that life, or the ingredients for life, can be transferred between planetary systems. The first hypothesis Loeb examined was natural panspermia. Could microorganisms or biological molecules have survived inside this interstellar iceberg during its multi-billion-year journey through the void between stars? The second hypothesis was what Loeb called directed panspermia, the idea, highly speculative but not entirely dismissible, that a technological civilization might deliberately seed life into a passing interstellar body as it enters a stellar system. Loeb was careful to present both as objects of scientific inquiry rather than conclusions. But the very fact that a Harvard astrophysicist felt the data justified publishing such questions in a scientific journal tells you something about what James Webb had actually found. The question about whether microbial life could survive the journey is one that astrobiologists have examined seriously for decades. The interior of a sufficiently large icy body provides shielding from cosmic radiation. Temperatures in interstellar space are close to absolute zero, which counterintuitively can preserve biological material by slowing or halting chemical degradation. Certain extremophilic organisms on Earth, tardigrades being the famous example, can survive conditions of radiation, vacuum, and extreme cold that would be lethal to virtually any other life form. Whether any organism could actually survive the billion-year timescales involved in an interstellar crossing is genuinely unknown. We have never tested it. We may not be able to test it within any time frame a living scientist can witness. But the question is not physically absurd, and the detection of methane in unusual quantities from an object 10 to 12 billion years old gave those who study such questions something concrete to discuss. And that age is where the story of 3I Atlas becomes almost vertiginously strange. The Nature paper published on June 22, 2026, authored by Martin Cordner and colleagues, entitled Isotopic Evidence for a Cold and Distant Origin of 3I Atlas, represents the deepest scientific excavation of this object yet achieved. The team used Webb's NIR spec instrument to simultaneously measure isotopes of water, carbon dioxide, and carbon monoxide in the comet's coma during the December 2025 observations. The numbers they found had no precedent in any solar system body ever measured. The water in 3I Atlas was enriched in deuterium, which is heavy hydrogen, at a ratio of 0, 98% plus or minus 0, 0.6%. Every known comet in our solar system shows a deuterium to hydrogen ratio orders of magnitude lower than that, more than an order of magnitude lower. To be specific, 3I Atlas carries approximately 30 times more deuterium in its water than any comet we have ever observed in our own solar system. Deuterium enrichment of this magnitude is a fingerprint of formation in extremely cold environments. When water ice condenses at temperatures below about 30 Kelvin, which is roughly negative 243 degrees Celsius, the deuterium tends to concentrate in the ice in a way that it does not at higher temperatures. The cold is not just a byproduct of interstellar space. It reflects where and when this object formed. Our own solar system formed from a molecular cloud that was already enriched with carbon-13, the slightly heavier isotope of carbon, because previous generations of stars had lived, burned, and died in the galaxy, and seeded the interstellar medium with carbon-13 as they did so. The ratio of carbon-12 to carbon-13 in our solar system reflects our sun's relatively recent birth, 5 billion years ago, after several generations of stellar processing of the material in our galactic neighborhood. But 3I's Atlas shows carbon-12 to carbon-13 ratios in its carbon dioxide and carbon monoxide that are dramatically higher than anything in our solar system. The range measured by Webb was 141 to 191 for carbon dioxide and 123 to 172 for carbon monoxide. Solar system comets typically cluster well below those numbers. These high ratios indicate that when 3I Atlas formed, the gas that built it had not yet been enriched with carbon-13 from stellar generations that had not yet lived. The universe is approximately 8 billion years old. This means 3I Atlas condensed from a planetary system less than 2 billion years after the Big Bang. Our Earth did not exist. Our sun had not yet ignited. The solar system that would eventually produce us was less than a whisper of potential in gas that had not yet clumped together. The implications of that age cascade outward in every direction. This comet, which traveled through the dark between stars at 58 kilometers per second for an unknown but almost certainly enormous span of cosmic time, spent some portion of that existence inside a planetary system that may no longer exist. Whatever star 3I Atlas originally orbited, that star was part of what astronomers call the Milky Way's thick disk, a population of stars formed earlier and from more metal-poor material than the thin disk where our sun lives. After the object was ejected from its birth system, likely by a gravitational encounter with a large planet or close stellar flyby, it entered the void. And, for billions of years, it drifted. The outer layers of its surface were steadily bombarded by cosmic rays, which cracked and recombined molecules, built up complex organic compounds in a mantle of processed ice and carbon, and slowly depleted the most volatile species from the very outer shell. The interior remained frozen, insulated, pristine. When it finally crossed into our solar system and the sun's warmth began peeling back those outer layers, it was as if a letter sealed 10 billion years ago had finally been opened. A companion study to the Nature paper using data from the Atacama Large Millimeter or Submillimeter Array, ALMA, along with the European Southern Observatory's Very Large Telescope, added further isotopic measurements of cyanide and other nitrogen-bearing species in the coma. These complementary measurements supported the same conclusion from a different molecular angle. The picture that emerged from all of this data combined is of an object born in a galaxy that looks almost nothing like the galaxy we live in today, formed under conditions of extreme cold and low metallicity that no longer exist anywhere near our solar system. Dr. Stephanie Millam, also from NASA's Goddard Space Flight Center and a co-author on the Nature paper, framed the broader significance in a statement that is worth sitting with carefully. She noted that the analysis of these interstellar objects is a major step toward learning how common, or uncommon, the conditions for the evolution of life actually are in the universe. We currently know of precisely one place in the entire cosmos where the chemistry definitely led to life. That place is Earth. Everything else is inference and calculation. But every interstellar object that passes through our solar system and reveals its chemistry gives us a data point in the larger statistical question of whether what happened here is typical or exceptional. The chemical fingerprint of 3I Atlas, with its enormous abundance of organic molecules, its methane, its methanol, its formaldehyde, its ethane, all of these molecules that on Earth are either produced by life or serve as precursors to the molecules life is built from, suggests that interstellar space may be far more organically rich than the inside of our own solar system's comets have led us to believe. There is a concept in astrobiology called the organic inventory, the suite of carbon-bearing molecules available to a young planet as the building blocks from which life might eventually emerge. Comets and asteroids are understood to have played a role in delivering organics to the early Earth. The late heavy bombardment period, roughly 4 billion years ago, when the inner solar system was being pummeled by impacts, almost certainly deposited enormous quantities of organic material onto the surface of our planet. Some researchers believe that impacts by water ice-rich bodies might have seeded Earth with the raw materials that eventually, through billions of years of chemistry and environment, produced the first living cell. If comets in our own solar system carry organic cargo, and we know they do, then an interstellar comet that shows 14% organic production relative to water, that carries methane in its buried interior, that was formed in a system that predates our sun by more than twice Earth's entire age, forces an uncomfortable and thrilling question. How many other planetary systems, over 13 billion years of galactic history, have been seeded by objects just like this one? The mathematical reality of the galaxy amplifies the question. It is estimated that there are roughly 10 to the power of 26 interstellar objects, like 3I Atlas, passing through stellar systems across the Milky Way at any given moment. That is a number so large it dissolves into abstraction. But the point is that this kind of chemical cross-contamination between star systems, the passive exchange of molecular cargo via ejected planetesimals crossing the void, is not a rare event. It is something the galaxy has been doing continuously for billions of years. Every system that forms planets also ejects material. Every system that ejects material seeds interstellar space with chemical messengers. Those messengers travel at tens of kilometers per second, and over billions of years they reach other systems. They pass through other solar warmths. They sublimate. They release whatever they were carrying. What 3I Atlas was carrying, as far as the chemistry can tell us, was a library of molecules that life on Earth either needs or produces. Methanol and formaldehyde are both precursors to amino acids, the building blocks of proteins. Methane is produced by life here on Earth in quantities that astronomers are now using as a target biosignature when they observe the atmospheres of exoplanets. Ethane is produced both photochemically and biochemically. None of these individual detections proves life. Let that be stated clearly. Not a single one of the molecules found in 3I Atlas is something that cannot be produced by ordinary chemistry without any biological involvement. But the combination, the ratio, the timing of the methane emergence from beneath an insulating crust, and the object's age, together construct a set of circumstances that serious scientists felt compelled to examine through the lens of panspermia. For the first time, not as a fringe idea, but as a legitimate scientific hypothesis being evaluated against real instrument data. What happened to 3I's Atlas after December 2025 is in some ways as telling as the measurements themselves. The comet continued outbound. By early 2026, it had already crossed Jupiter's orbit and was receding beyond the practical limits of observation. Matthew Belyakov, the lead author of the MIRI methane paper, noted that Webb was scheduled for one additional observation of the comet in spring 2026, but that by then it was already extraordinarily difficult to observe. Every day that passed, 3I Atlas moved further away, its coma fading, its signals weakening, the window closing. The Nature paper, published June 22, 2026, was in many ways a culmination of a race against orbital mechanics that scientists had been running since July 1, 2025. 11 months of observation, data collection, analysis, peer review, and publication, compressed into a span defined not by institutional timelines, but by the inexorable physics of a hyperbolic trajectory. The comet is now heading toward the constellation Gemini, moving outward through the outer solar system and eventually back into the interstellar medium. It will not return. The orbital integration of 500 statistical clones of 3I Atlas, a modeling exercise designed to capture the uncertainty in its exact trajectory, showed that it is leaving the solar system at a mean radial velocity of approximately 58, 1 kilometers per second, nearly identical to the speed at which it arrived. The gravitational influence of our sun and the planets did not capture it. Nothing could. An object moving that fast on a hyperbolic orbit passes through a stellar system the way a bullet passes through water, disturbed but not stopped. Somewhere in the direction of Gemini, in a few million years, 3I Atlas will be moving again through the silence between stars, carrying whatever it carries, perhaps eventually reaching another star system where, if there are instruments capable of seeing it, observers very different from us might ask the same questions we just spent a year trying to answer. To fully appreciate what 3I Atlas has told us, it helps to compare it directly with its two predecessors and understand why neither of them gave us anything close to this level of insight. Oumuamua, the first interstellar visitor, gave us essentially nothing in terms of molecular chemistry because it produced no detectable coma at all. Whatever it was made of remained locked inside. Borisov II behaved more like a conventional comet and gave astronomers their first taste of interstellar chemistry. But the instruments available in 2019 were far more limited than what Webb and Spherex brought to bear in 2025. Borisov was studied, characterized, and ultimately described as compositionally similar to solar system comets, which told us something but raised no radical questions. 3I Atlas is the first interstellar object to arrive at precisely the intersection of maximum observational capability and maximum compositional strangeness. Its carbon dioxide abundance, its methane, its deuterium enrichment, its age, every parameter sits at an extreme. And unlike Oumuamua and Borisov, which were caught relatively late in their passages, 3I Atlas was detected early enough that telescopes could follow it continuously from approach through perihelion through outbound retreat, tracking how its chemistry evolved as solar heating progressively unlocked different layers of its interior. The timeline of which molecules appeared and when was itself scientifically rich data, and no previous interstellar object gave us a timeline anything like that. The broader connection to exoplanet science is one that researchers were quick to draw. When astronomers used the James Webb Space Telescope to study the atmospheres of distant worlds orbiting other stars, they search for what they call biosignatures, chemical signatures, whose presence in an atmosphere is difficult to explain without invoking biological processes. Methane is one of the primary targets on that list. The detection of methane in a planetary atmosphere, especially when paired with other oxidizing gases like carbon dioxide, is considered a potentially strong biosignature because abiotic chemistry tends to consume methane rather than produce it at scale. What 3I Atlas demonstrated is that methane can be carried in frozen form across interstellar distances, delivered to a stellar system by a passing icy body, and released into the local environment during a solar encounter. The presence of methane in a planet's atmosphere may therefore reflect not only what biology is doing on that world right now, but also what interstellar chemistry delivered to that world at some point in its history. The James Webb Space Telescope represents the most powerful tool our civilization has ever built for the specific kind of spectroscopic chemistry it performed on this object. Its ability to resolve isotopic ratios in a comet's coma at a distance of hundreds of millions of kilometers, to detect methane in a diffuse gas cloud being actively blown away by the solar wind, to distinguish between carbon-12 and carbon-13 in molecules that exist only briefly before escaping into the vacuum, is a capability that simply did not exist before Webb became operational. When Oumuamua arrived in 2017, we watched it leave without understanding what it was made of. When Borisov arrived in 2019, we did better, but the instruments of the time could not approach the sensitivity that Webb brings. 3I Atlas arrived at exactly the right moment in the development of our observational capability. And the universe apparently decided to send us one of the most chemically interesting and ancient interstellar bodies we could have hoped to encounter. The question of life in 3I Atlas has no definitive answer. The data does not prove life. What it does, with extraordinary scientific precision, is prove that the chemistry associated with life is not confined to our solar system, is not confined to our epoch of cosmic time, and is not even confined to the relatively young and heavy element-rich corner of the galaxy where we happen to live. The organic molecules found in 3I Atlas formed in a stellar system that predates our sun by more than twice Earth's entire age, in a cold, radiation-soaked cloud around a metal-poor star that may no longer exist. Whatever chemistry was possible in that environment produced methanol, methane, formaldehyde, and ethane. Those molecules then survived more than 10 billion years of exposure to the galactic environment, buried beneath insulating ice, preserved at temperatures close to absolute zero, waiting, as if waiting is the right word for a process governed entirely by physics, for a star warm enough to unlock them. There is a profound philosophical weight to the fact that this is not speculation. This is not the premise of a science fiction story. This is data published in Nature, measured by instruments operated by NASA and ESA, subjected to peer review, supported by independent observations from multiple telescopes on the ground and in space. A piece of another planetary system born before our sun existed, carrying a chemical inventory that overlaps meaningfully with the chemistry of life, passed through our neighborhood, and we were watching closely enough to read it. We had the tools. We used them. And what we learned is that the galaxy has been running chemistry experiments far older and far stranger than anything our own solar system can account for. Whether life itself has ever hitched a ride on objects like this one, whether the molecules we detected represent the aftermath of biology or merely the preconditions for it, that question remains genuinely open. But it is no longer purely theoretical. It is now a question that actual data demands we take seriously. Martin Cordner put it this way when the Nature paper was published. He described 3I Atlas as a unique opportunity to study an ancient object from the distant galaxy, probably predating our sun and solar system. That description, technically careful and scientifically modest, nonetheless contains something extraordinary. We did not just observe an interstellar rock. We looked back across 10 to 12 billion years of cosmic time through the chemistry of a frozen body that crossed the galaxy to reach us. And in it, we found the kinds of molecules that, on the only world we know to harbor life, are produced by the living and used to sustain the living. The universe, it turns out, has been stocking the interstellar medium with the raw materials of life for most of its existence. And 3I Atlas is the most ancient, the most chemically strange, and the most scientifically instructive messenger it has ever sent our way. The comet is gone now. It entered our solar system as a mystery, and it left as a data set that will take researchers years to fully interpret. But every time a survey telescope like Atlas scans the sky at 3 a.m, every time it catches a faint smear of light moving too fast to belong here, we are given another chance to read one of these ancient letters from the galaxy. The question is no longer whether the ingredients for life travel between star systems. The question is what, if anything, was alive when those ingredients were packed.